our PCS IBS seminar. We are very happy today to have with us Dr. Joe Huxford from Toronto University, Canada. And our scientific host today is Zung, who will introduce our speaker. Please, Zung.
Okay, so thank everyone for coming. Today we are very happy to have Dr. Joe Huxford from Toronto University. Joe did his PhD with Professor Steve Simon at Huxford University. After finishing his PhD, he moved to Canada as a postdoc researcher, worked with Professor John Bijkgraaf that we all know. And today we will have a talk by Joe on lattice gate theory. And Joe, please take the place.
Okay, thank you for the introduction. Yeah, so I'm actually going to talk to you today about some work I did with them here and also with Jonbeck about these generalized loop braiding statistics in 3D topological phases. So to give a bit of a sense of the structure, I know this is a fairly niche topic, and so I want to talk a bit about the background of this before we get started. So I'm going to talk a bit about topological phases of matter in 2D and in 3D. And I'm also going to give a brief recap of the toric code because I'm going to be comparing these more advanced results to that throughout. Then I'm going to talk about this twisted lattice gauge theory model, what it is, talk about the excitations we get, the braiding relations, and the conserved charges that are present. So when we talk about topological phases of matter, there's a bit of a disambiguation to be given because there are a couple of different things we could mean. But here what I'm really talking about are long-ranged entangled phases, which are really characterized by this entanglement structure between the local degrees of freedom. So this is quite different from how we think of ordinary phases in terms of symmetry breaking and spontaneous symmetry breaking, Although I will say as a side note, I'm sure you've probably heard quite a lot about this recently with Zung here, is that there's been some more thought in terms of topological phases in terms of generalized symmetries and generalized symmetry breaking, but that's not what I'm going to talk about today. So this entanglement results in many of the unique features that we see in these topological phases, such as a robust kind of topological ground state degeneracy, fractionalized charges on the excitations, as well as non-trivial braiding statistics. And these aren't just kind of theoretical constructs, these are being observed in experiments. So in particular in the quantum Hall system, of course, but also more recently in kind of synthetic phases like trapped ion processes. Quite recently, there was this paper where they actually realized non-abelian topological order and braiding. So in particular, the features I'm most interested in for the topological phases is their excitations and their exchange statistics. So in 2+1d, these excitations are called anyons because they have these exchange statistics that have any phase, so they generalize fermions and bosons. And so if we have a couple of particles in this 2D plane, and we take one of them on a path all the way around the other one, then we pick up this phase. In the case of bosons or fermions, we pick up the exchange phase squared, so that's plus or minus 1 squared, which is just 1. But for an anion, we can have a general phase, or even a unitary transformation and some internal space for the particle, in which case it's a non-abelian anion. And these can also, for anions, be different particles. They don't have to be identical particles, in which case they're mutual anions. And this has this kind of topological structure, which we can see by looking at the world lines of these particles. So in this case, we're having a process where one of these particles remains stationary, so it just has this vertical world line, while the other one goes on this path that kind of encircles it. And the point is, there's no way to smoothly deform these world lines to disentangle them, and that gives the kind of topological nature of this exchange phase. It's not sensitive to any smooth deformations of this world line, it's just the topological component from the kind of class of these paths. On the other hand, in 3+1d, we might think that there's not that much going on because if we have this kind of exchange path, we can smoothly deform it into a trivial one. So because we're no longer locked to this 2D plane, we can take this exchange path, and we can just pull it up in the vertical direction and over this blue particle and just contract it to nothing. And then because this is supposed to be a topological property, it should be invariant under these smooth deformations. And this tells us that this phase has to be trivial. And this results in the familiar bosons and fermions. So in that case, you might be asking, why am I even talking about these phases in 3+1d? And that's because we have access not just to point-like excitations, but also to loop-like excitations, which gives us these more generalized exchange statistics. So in particular, two basic types of these braiding moves is one where we take a point-like particle and we move it up on a path that kind of links with this loop-like excitation. So we're pulling a point-like excitation through a loop and back around. And we can do something similar with a loop. So this is like a series of snapshots, like a time lapse. We start with two loop-like excitations vertically separated, and we can just pull one of them up and through the other one, like so. But actually, recently, people have been realizing that this isn't the whole story yet, because these loop-like excitations have a somewhat unique property compared to point-like ones, where they can actually be linked together, and that significantly changes their character. So in fact, instead of this kind of two-loop braiding process, we should be looking at something called a three-loop braiding process, or necklace braiding, where two loops braid while they're linked to a third loop called the base loop. So here, this is the same two-loop braiding process I showed you earlier, except that now both of these loops are linked to this existing base loop here. So I've told you about some of the features these excitations have, but then the question is, how can we study this? And one way that this is done is through exactly solvable models, which are often made from commuting project operators. So this is something that's been used in both 2+1d and also 3+1d. So in 2+1d, we have the toric code, which I imagine many of you are familiar with, but also things like string net models. And in 3+1d, we have various types of lattice gauge theory, higher lattice gauge theory, twisted gauge theory, and Walker-Wong models. And I'm going to talk to you about one of those today. But first, we should give a brief recap of the toric code and some of its features. So in this case, we have our spatial degrees of freedom are discrete. They're on some graph. Here we're taking the square lattice, and there's a z2 variable for each edge of the graph. So we just label each edge of plus or minus 1. Then our Hamiltonian consists of two types of terms. We have terms for the vertices of the lattice, and we have terms for the plaquettes of the lattice. And these are going to correspond to terms that enforce a zero flux condition for the plaquettes or a zero charge condition for the vertices, which we'll see in a second. So the plaquette term is fairly easy to understand. If we apply it on some plaquette, here we've got a square with 4 edges. It's just going to check what the product of these edge labels is. So remember, these edge labels is plus or minus 1. And if the product of these edge labels is 1, it's going to return back the same state. And if the product is minus 1, it's going to annihilate that state. And then because this enters the Hamiltonian with a minus sign, this means that the lower energy state is the one where this product is plus 1. And for the toric code specifically, there's a nice kind of visual way to represent this, where we denote the downspins or the minus values by solid lines and the upspins by dashed lines. And what we'll see is that this plaquette term enforces that the ground state is made up of closed loops in the dual lattice. So what I mean is we have some configuration like this, and then if we draw a path that intersects through, that bisects these edges, this path is going to form a closed loop here, and then another closed loop here. On the other hand, what the vertex term does is it actually fluctuates the edges around the vertex. So here we have some vertex, it's in the neighborhood of 4 edges. And so when we apply it, what it does is it gives us a half. It's going to give us the original state plus the same state, but where all of these edge labels are multiplied by minus 1. So we can think of this as kind of inserting a closed loop or a closed dual loop. And this is going to fluctuate our configurations of closed dual loops to make a kind of massive linear combination of all of these possibilities. And what this results in is as having two different types of excitation, or two basic types of excitation from which we can build all of them. So we have electric excitations which violate the vertex terms, and magnetic ones which violate the plaquette terms. And these can be fused together to get a dionic excitation, where it's sort of fermion, or we can have a trivial particle where there's no excitation. And that gives us 4 types in total. And this is actually the same as the ground state degeneracy on the torus, which is no accident. And for these kind of models, we generally expect this. So there's a correspondence between the number of types of excitation and the ground state degeneracy on the torus. So now, how can we study these excitations in this model? Well, we can look at their creation operators, which in this case are ribbon operators. So for example, the magnetic ribbon operator is a string of Pauli X operators on some dual path in the lattice. So if we start with a state where everything is in the up state, and we apply a Pauli X operator here, well, this is going to mean that we now have a -1 for this plaquette, because it has 1 downspin, so the product of edges around here is -1, and so it's going to be excited, and the same for the neighboring plaquette. If we then apply a second Pauli X operator on this edge, what we're going to see is that this actually then satisfies this middle plaquette, so it's no longer excited, and instead the excitation moves to this third plaquette here. So here we have a ribbon here that passes through these 2 edges, and we have 2 excitations at the 2 ends of this ribbon. And then the electric ribbon operator is kind of similar, except that instead of Pauli X's, it's going to be Pauli Z's, so it's just going to measure the spin, and instead of being applied kind of in the dual lattice, it's just applied along a path in the direct lattice. And so our ground state is this kind of linear combination of these closed loop configurations, closed dual loop configurations, with equal weight. These pluses are all the same, but when we then measure this edge here, we can introduce minus signs into some of the configurations where there's a downspin. And what this does is it excites the 2 vertices on either end of this path. And these ribbon operators are useful for various things, but in particular, they allow us to obtain the braiding relations of the electric and magnetic particles. So this is because if we imagine creating a magnetic excitation of some magnetic ribbon operator here, and then we take an electric ribbon operator and we pull it around, so this is going to make a pair of excitations and move one of them around this path. Then because this is a string of Pauli Z's and this is a string of Pauli X's, they're going to anti-commute if they intersect, and this gives us the braiding phase of -1. Actually, these ribbon operators have various nice properties. One of them that's quite important is the fact that they're topological, which kind of preserves this topological nature of the braiding phase that I've discussed before. So if we imagine we start with the ground state, here we're just representing the ground state for this particular fragment of lattice, where it's this sum of closed loop configurations. And we can apply magnetic ribbon operators in 2 different locations. So they're all both going to start at this plaquette and end at this plaquette. But this one is going to take this horizontal path, and this one is going to take this kind of U-shaped or N-shaped path here. So if we imagine acting a bit on this particular configuration, we flip these 2 spins and we get this state. And if we act a bit on this one, we're going to get this state, and so on. But then if we apply the ribbon operator in the other location, and by acting it on this state, we're going to get this state here in the bottom left. And we can see that this is the same as the right-hand state from ribbon 1, and also this second state here, the middle left state for ribbon 2, is the same as the middle right state for ribbon 1. And so when we take a look at the action on this full linear combination, actually these are producing the same state. So this shows that the actual precise position of the ribbon isn't that important, and we can say that a ribbon is kind of invisible. We just see its excitations at the ends. Now what about 3+1d? Well, while much of what we've talked about so far can be imported, we can consider commuting projector models, we can consider creation operators. Because some of the excitations are loop-like, we need something other than ribbon operators to make them. And this is where membrane operators come from. So these are operators applied on some surface on the lattice, rather than just along a path like the ribbon operators. And then there are various different shapes of membrane we can use. So if we use a spherical membrane, it has no boundary, and so it doesn't produce any excitations. If we use a hemisphere or a disk, it just has a circular shaped boundary, and so it's going to make one loop-like excitation. Or in this case, we can apply it on this red cylinder, and it has two open ends, and so it's going to produce a pair of loop-like excitations. And this is particularly important because we can actually apply this membrane operator in a way that's linked to an existing excitation, like this green loop here, without the membrane operator intersecting this green loop. And so this is going to be useful when we can consider the free loop braiding, because this lets us make excitations linked to other excitations. And so the general picture for what we wanted to do was take the membrane operators and use them to calculate the various properties of the excitations. That includes their braiding relations that we've discussed in some detail, but also the conserved charge they carry and the fusion relations, which describe how we can combine different excitations into one. At this point, I should note that this is one way of studying topological phases. It's not the only one. There are lots of indirect methods that have been used, like dimensional reduction and tube algebra. And indeed, many of the results that we've obtained have been obtained before, but we wanted to obtain them in this kind of more unified way, starting from the membrane operators. And so that's kind of the prelude out of the way. And now I'd like to discuss the particular model we had in mind. So I don't know if there are any questions at this point, or if I should just... Well, anyway.
Maybe I have one question.
Yep.
Do we have some sort of like another version of toric code with I think the ends would work, but how about like some continuous group? We have some version of toric code, but with
So you can generalize it with a discrete group, with any discrete group, of course. In which case you have something called the quantum double model. But for continuous groups, you run into a bit of a problem just because you don't have this kind of infinite dimensional Hilbert space.
maybe it's also like we don't have the gap phase of, let's say, U1 symmetry.
Yeah, so people have considered a kind of U1 K symmetry as well, which is kind of similar in character, sure.
So I think we don't have the toric code, but we can the same. Okay, thanks.
Okay, so then we're considering this modeling on 3+1d, and it's going to get a bit more technical from here on, I'm afraid. But this is a Hamiltonian realization of something called the Dijkgraaf-Witten topological quantum field theory, which is a very well-known and highly used field theory. But this particular Hamiltonian version was introduced by Witten et al. In 2015. And these Dijkgraaf-Witten models, or these Hamiltonian versions, are important because they're believed to realize all 3+1d bosonic topological orders that can be realized by these types of models, where the point-like excitations are only bosonic, so there are no point-like fermions. Much like the toric code, we're going to represent space by a discrete structure, in this case a triangulation. So this is just like our graph from before, but instead of having the square plaquettes, we're going to only have triangular plaquettes, and the kind of smallest 3D units of space are going to be tetrahedra. But again, time is going to be continuously controlled by a Hamiltonian. So this is really a family of models where each model is defined by a finite group G along with a Fourier cycle. So the group G is going to label the edges. It's like the Z2 from the toric code, but now it's some more general finite group. And this four-co cycle, I'll talk a little bit more about in a second, but it's a function. We can basically just think of it as a phase. It's a function from 4 group elements into U1. And we took G to be abelian for the most part, although some of these results can be extended to non-abelian groups. So this four-co cycle, as I've said, is a function from 4 group elements to a phase, but it has this additional constraint called the four-co cycle condition. And this might seem like a somewhat arbitrary condition, but I just wanted to mention that it does have a geometric interpretation in terms of 4 manifolds, where it makes sure that a Dijkgraaf-Witten theory on 2 different representations of the same manifold give the same theory overall. So then the Hamiltonian has a kind of similar structure to the toric code, where we have vertex terms and plaquette terms. So the vertex term is an average over gauge transforms, and we can kind of think of this as inserting a surface with some like flux labeled G. So it's a bit like the toric code one, where it's inserting a loop. In that case, we only have one non-trivial group element. So it's fluctuating the edges that are around the vertex V, but the co-cycle twist enters here because we also apply a phase for the surrounding tetrahedra. So we have a phase that depends on the labels on the surrounding tetrahedra and on the four-co cycle. On the other hand, the plaquette term is basically the same as the plaquette term from the toric code, except with this more general group G. So it forces this flatness or zero flux condition, where if we take a path all the way around the plaquette, that path should have a trivial group element associated to it. And for the excitations, again, a bit like the toric code, there are 2 classes of excitation. We have electric excitations, which are point-like and only excite the vertex terms, and we're not going to talk very much about them here. They're kind of labeled by representations of the group, and they behave the same regardless of the four-co cycle twist. On the other hand, the magnetic excitations are loop-like and excite the plaquette terms, although in this case they can also excite vertex terms, and we should probably call them dionic excitations because they can carry both charge and flux. So these are the ones that we're going to focus on for the rest of the talk. So these are produced by membrane operators, as we've said earlier, and the membrane operators that can be labeled by a flux label, which is just an element of the group, and a charge label, which we'll describe more later. Geometrically speaking, they act in a region of the lattice, which we can think of as a kind of thickened membrane, or as consisting of 2 kind of adjacent membranes. We have the direct membrane that lies in the direct lattice. So this means it kind of contains edges and vertices. Edges lie parallel to the direct membrane. Whereas the dual membrane is going to bisect edges. It's going to cut through them. This is like how the electric ribbon operator in the toric code acts along a path in the lattice, whereas the dual membrane, the ribbon operator for the magnetic excitation in the toric code it bisects the edges of the lattice, or you could say acts in the dual lattice. Then going a bit more into the algebra, this magnetic membrane operator can be decomposed into 3 parts, which we're going to talk a bit more about in a second. So we have these 2 parts that only depend on the flux label H, and then we have the surface weight, which depends on both the flux and the charge, which we'll describe in some detail. So this first part is independent of the co-cycle, so it's the same regardless of whether the co-cycle is trivial or whether it's non-trivial, and it doesn't carry any charge. So all it's going to do is multiply edges cut by the dual membrane by H or H inverse, and it basically produces the plaquette excitations. So as a kind of schematic for this, we can imagine if we start with our ground state and we take one edge on our lattice and we multiply it by H, well, this is going to excite the surrounding plaquettes because now the product of edges around this plaquette is going to be non-trivial rather than being the identity element, and so these are all going to be excited. And we can think of these excited plaquettes as lying on the loop that just encircles this edge here. Now we might say, okay, well, we can take this plaquette and we can modify another edge on it. We can multiply its label by h. And this is going to remove this excitation here, because now the total product around this plaquette is the identity again. And so you can see it's no longer excited. But by doing this, we're exciting all of the other plaquettes around this edge. And so we're basically growing this loop-like excitation. And repeating this process, we just grow it further. And we end up with a loop-like excitation consisting of a series of plaquettes on the boundary of some membrane, which would be in the middle here. But there are no excitations in the middle of the membrane, so there's nothing here or here, for example. And we can even grow it perpendicular, like so.
Joe, can I ask something? So,
Yes.
picture you show here squares, but you have triangles, right?
Yes, I'm sorry about that. I thought it would be easier to show with squares, because
Just for presentation purposes.
Yes, so in the actual lattice we'll have triangles. I should have said that.
Mm-hmm. Okay, thank you.
So then we have this dual phase, which I'm not going to talk much about. It's a phase that depends on the tetrahedral dual membrane, but it's basically just fixed. It's demanded by this 4-co-cycle twist, and we just need this additional phase because this phase is also in the vertex transforms, and so we need a compensating phase to ensure that it commutes with the vertex transforms. But there are no additional degrees of freedom associated to it. And when we were actually looking for it, we just used the principle that the membrane operator kind of looks locally like a series of gauge transforms, like we're inserting a sheet of flux. And so it should look locally like the vertex transforms so that it commutes with the vertex transforms. And finally, we have the surface weight, which we'll talk about in a bit more detail, because it carries information about both the topology of the membrane on which we're applying the membrane operator, as well as the charge label. So we're going to start with our direct membrane, which is some more complicated structure, some complicated membrane in our lattice, like this one here. The red is the boundary. And we're going to just start by taking a diagrammatic representation of it. So we're just going to take a plan view, basically. And remember, each one of these edges, in principle, is labeled by a group R. And now the surface weight is, in principle, a function of every edge label on the surface, which is obviously a complicated function. However, in order to commute with the vertex terms in the bulk of the membrane, because remember, we only want to create excitations on the boundary of the membrane, the form of this surface weight is highly constrained. In particular, we can show that the weight of a complicated diagram has to be related to the weight for a much simpler diagram via a set of graphical moves. This is something that's been seen in some other models, like a C2Z2 model by Lim. So these graphical moves might be familiar to some of you because they're just bistellar flips or Pachner moves, which are moves that allow us to change how a surface is triangulated. So in particular, we have this 2-to-2 move, which just changes how these 4 vertices are connected. And then we have this 3-to-1 move where we're removing a vertex. And this can kind of be thought like pulling the surface over a tetrahedron. And when we do this, we have to pick up a phase that's determined by the labels on this tetrahedron. And it turns out that this phase is given by a 3-co-cycle, which kind of descends from the 4-co-cycle via this product here, which is called a slant product. And then by using these graphical moves, we can reduce this complicated diagram to just some simple set of diagrams, which we then have to manually assign a weight. And this weight is the charge label that we've been discussing. So which diagrams we actually need depends on the topology of the membrane. And this is because we're not allowed to remove any of the vertices on the boundary of the membrane. These are kind of fixed. They're not touched by the graphical moves. So if we have a disk, something like this, the whole thing is the boundary. And so we can just remove these 3 internal vertices. If we have a cylinder, then the top and the bottom edges are identified, and the boundaries are these 2 red edges. And we can simplify it by removing all of these vertices. And we're left with a kind of local structure along the edge that depends on the number of vertices on the edge. And then this more universal global structure in the middle, which is this kind of hourglass shape here. And then for the torus, all of the whole thing is bulk, so we can remove every vertex except one, which we need just to keep the structure of the torus intact. And it's worth noting that the labels of these are going to depend on existing excitations in the system in the way that I'll describe in a second. So then, when we apply this procedure, this gives us a form for the surface weight, where, okay, it's some function of every edge on the diagram, but then that's actually some known function times this weight for the simple reference diagrams. Or here we've taken a case of a cylinder. And so different choices for this weight are going to give us different operators, which is why it's like an additional label, it's the charge label. So the most interesting ones for us are cylindrical membrane operators. And the reason is, sorry, go ahead.
Can you go to previous slide?
Yeah.
So when you do the move of when you do the move in the graph for the ZN case, does this move commute or not?
Does this move do what, sir?
Move. I mean the removing of the point. Is this commute or not? There's the 2 to 2 and 3 to 1. Can you do this like different order and get the same result for the ZN case?
Oh, they all commute. It doesn't matter which order you do this in, you'll get the same phase at the end. But as long as you end up with the same diagram at the end. Yeah, that's a kind of consistency condition, I guess, which is guaranteed by the pentagon equations, I guess. Or in other ways, it's guaranteed by the co-cycle condition, the free co-cycle condition that's that this object satisfies. That's what guarantees that they. It doesn't matter which order you do them.
Yeah, that's true. Yeah.
And so, yes, we're particularly interested in these cylindrical operators because they make these loop-like excitations that are linked to that can be linked to an existing base loop. And so if we take the diagrammatic representation for this membrane, which would be something like this, where again these two edges are identified, if we apply it when it's linked to this existing base loop here with flux label K, then this edge here, which is the cycle of the cylinder, has to match the label of this excitation. So this edge is fixed to be K in all of our reference diagrams. On the other hand, the length of the cylinder, this is an open path, so it's not fixed in any way, and it's not going to be, the ground state isn't going to be an eigenstate of this operator, so this is going to be in some linear combination of states. And so we've discussed how we have this weight, this V, and we're allowed to choose any value of this for all of the different reference diagrams. But we can find some sensible basis for it, which is going to give us nice properties. And the simplest way we can find this is by using composition rules. So in the toric code, if you take a magnetic ribbon operator and you attach another magnetic ribbon operator to the end of it, so you join two of them end to end, they fuse together and you just get a single magnetic ribbon operator. And we're going to just demand the same is true for these cylindrical membrane operators. So if we apply two of the same charge and flux labels end to end, they're going to fuse to give us a single cylindrical membrane operator. And we'll, sorry. Yep.
Because like, so is this like, it's more like apply some ribbon operator rather than merging, right?
It's like a ribbon operator, I guess, in that one of the directions is kind of compacted. So this label is kind of fixed. The label of this cycle is fixed by the label of the base loop. So you're just left with the one.
Yeah, so I think that this said it looked similar, like we apply a ribbon operator for it rather than to.
Yeah, it looks a bit like that, that's true.
And then what's the process if we have two membrane but different type? It not connect, but then that means we need to consider two separated membrane operators rather than connect them, right?
Yeah. So for the different types, we can't connect them in this way. But anyway, what we find is that the sensible basis is actually given by projective irreps of the group G. And then they have an internal space given by matrix indices. But for those of you who aren't familiar, projective representations are much like linear representations, except in the composition rule we have an additional phase factor. And in this case, this phase factor is this function, which is a 2 cocycle, which again derives from the 3 cocycle we found earlier, like this, and the 3 cocycle derives from the 4 cocycle. So it's a double slant product in the 4 cocycle. And if we consider this phase factor as a function of x1 and x2, which are the arguments of the two irreps, we see that the function depends on these labels k and h, where k is the label of the base loop, and h is the label of the flux label of our excitation. And in particular, if we take this base loop to be trivial, this 2 cocycle is also trivial, and so we just get ordinary linear representations back. But the fact that this phase factor depends on the base loop and the flux actually means that the objects, the charge labels, which ones were allowed, depends on the base loop. In other words, excitations with different base loops are distinct excitations. In addition, projective irreps can be higher dimensional even when the group G is abelian in a kind of limited way. What this means is that these irreps have this internal space given by matrix indices, and this leads to non-abelian excitations even for an abelian group. So we'll see that in the braiding relations in a second. That means that instead of just getting a phase for braiding, we're going to get a unitary transformation of this internal space. So if we consider, again, we're going to get the braiding relation from a commutation relation of membrane operators, just like for the toric code, we got it from a commutation relation of ribbon operators. And so if we have these two, we have this situation here where we start with a base loop K, we apply this red membrane operator that's going to produce a pair of excitations, and then we make this blue membrane operator with this complicated shape. What this is going to do is make a pair of loop-like excitations, pull one of them through this left-hand red loop, and then pull it back over. So it's going to implement a braiding procedure. And then the commutation relation here is basically matrix multiplication by the projective irreps. So we have the projective irrep alpha 2 KH2, which labels the membrane M2, but then its argument is the flux H1, which is the flux label of the other membrane. And so in the 1D irrep case, this leads to just a phase, alpha 2 KH2 of H1, alpha 1 KH1 of H2. But more generally, these are instead matrices that are acting on our membrane operators, acting on one of the indices of the membrane operators, because each index represents the internal space of one of the pair of particles made by a membrane operator. And so we see that we actually get, as he said, non-abelian braiding even for an abelian group. So that's everything I want to talk about for braiding. So if there are any questions at this stage, otherwise we'll move on to talking about this conserved topological charge. blue. So another important property of these excitations is their topological charge, which is a conserved charge, and it's something that can't be changed by any local operators. On the other hand, it can be measured by operators that enclose the excitation. So this is analogous to Gauss's law, how we can measure the charge in some region by measuring the electric field through a surface that encloses that region. So going back to the faithful toric code, we can see how this works out. We have here a magnetic ribbon operator which is going to produce a pair of magnetic excitations. One of them is somewhere off the screen and one of them is here. Now we can imagine applying a closed electric ribbon operator that encloses this excitation here. And we know from earlier that these are going to anti-commute because the magnetic ribbon operator is made from Pauli X's and the electric ribbon operator from Pauli Z's. We also know that this closed electric ribbon operator, if it acts directly on the ground state, just returns the ground state. It acts trivially on the ground state. And this allows us to define projection operators half 1 plus minus SR. So a linear combination of the identity operator and the electric ribbon operator. And then taking this 1 minus SR operator, if we act with it on our state, which is just the magnetic ribbon operator acting on the ground state, that's our example, then we're going to return the same state. This is because the SR is going to anti-commute the CT to swap to 1 plus SR, and then that will just act trivially on the ground state, and so we get CT of ground state. On the other hand, if we act this projector directly on the ground state, we're going to get 0 because the SR will give us 1 when it acts on the ground state, which will cancel with the 1 here. And so what we see is this is a projection operator that projects onto the sector where we have some non-trivial magnetic flux enclosed by the ribbon. In other words, it detects non-trivial magnetic flux. And we can do the same for electric charge, where we'd instead use a closed magnetic ribbon operator. And then these projection operators are also connected to the ground state degeneracy, because we can apply them on a non-contractible loop of the torus. And we can think of this as kind of like cutting open the torus and detecting the ground states through their kind of threading flux. And this leads to a number of projectors, which is 4, so that's the 2 magnetic ones, the trivial and non-trivial, multiplied by 2 electric, the trivial and non-trivial, being 4, which is equal to the ground state degeneracy of the torus. So again, the number of types of excitation is equal to the ground state degeneracy of the torus. And we can do something quite similar in 3+1d, but whereas in 2+1d the projectors were these closed ribbon operators, in 3+1d we're going to make them out of closed membrane operators. And we have a few more options in 3D, because we have surfaces of different topology. So we can choose a spherical surface, which is going to measure what we call a point-like charge, which can be carried by point excitations or loops, but it's not sensitive to the loop-like character. Or we can apply a toroidal surface, which is going to measure the loop-like charge. So because it has these non-contractible cycles, it's actually sensitive to the flux around this loop. But it's also sensitive to any links that we may have. So if this loop-like excitation is linked to an existing one, it'll actually have a different charge to if it wasn't. Again, reflecting this idea that linked excitations are fundamentally different from their unlinked cousins. And what we find for these projection operators when we construct them is that they're labeled quite similarly to the magnetic membrane operators by 2 fluxes, G1 and G2, along with a projective irrep alpha G1, G2. And this is good because this is the same labeling scheme as for the ground state degeneracy of the free torus found by this paper by Wang that constructed the model. So again, we have this correspondence between the ground state degeneracy and the number of excitations. This time it's the ground state degeneracy on the free torus and the number of excitations that can be measured by the 2 torus, which kind of clears up. So we've only shown it for this model, but this kind of clears up. There was a bit of confusion early on when people were considering 3D phases because they were counting the number of loop-like excitations, and they were like, well, it doesn't match the ground state degeneracy on the free torus. And that's because they weren't considering linked excitations. So just to summarize, we've constructed the membrane operators that produce loop-like excitations in this particular exactly solvable model. And this includes loops that can be linked to existing base loops. We've seen how these can be used to find braiding relations. And we found that the free loop braiding process is described by projective irreps, which also label the excitations. And we've established a connection between the number of projectors or types of topological charge and the ground state degeneracy on the free torus. So that's everything I'd like to say. I'd just like to acknowledge funding by the Natural Sciences and Engineering Research Council of Canada. And I've also put my collaborators' funding sources here. So I'll just leave you with my references and let me know if you have any questions.
Okay, thank you, Joe, for this nice presentation.
Thank you.
Have time for questions.
Does this is some notion about material systems that can be applied?
Sorry, could you repeat that?
Yes, material.
Between connection of theory and some material system and experiment.
All right, yeah, so this is something that's quite far from current materials realization. So both in terms of synthetic phases and in terms of actual materials, it's quite hard to find topological phases, let alone 3+1d ones. So we're really hoping that this is something that maybe could be found in the future.
I think that we have a comment also from our referee, right? So the contribution of the paper is that we introduce more way to realize more way to realize the phase of the bosonic system if it happens.
Yeah, the point is more to explore what kind of phases are possible rather than have a particular material realization in mind, at least for now.
Basically, the thing is that the contribution is that if there's like new bosonic phase, then basically our contribution is provides more kind measurement for this bosonic topological phase, I think. But yeah, I think that I agree with you that this is more mathematics rather than the real material.
Yeah, I mean, I guess hopefully it's not just mathematics, but that's not something that we...
Now that most of the work in this direction is very mathematical. Most of the work by Saugang and company. Right?
Yeah, the point is kind of to see what kind of features these phases might have.
Recently, they have a field theory paper realize the lattice model that proposed. So the field theory version is already done recently by Yang Peng. If there's no more questions, so thanks again.
Thank you.
Can you share with me your slide?